So good morning, and I would like to thank the organizer for giving us the opportunity to present our work. Can you hear me? I hope. And our work is about data augmentation and transfer learning approaches applied to facial expression recognition. A work written with my colleagues Leonardo, Rigutini and Claudio Saccà in QuestIT Research Lab, Siena, Italy. This is the main of this presentation. I give you an introduction, and I will talk about the dataset used for this work, image preprocessing and augmentation, the model and training algorithm. I give you the result of some experiments, and finally the conclusion and future perspectives. Since face expression is the first thing we pay attention to when we want to understand a person's state of mind, facial expression analysis represents the first step in researching and building a human emotion classifier. And the task that we analyze is how it is possible to understand in an automatic way the emotion felt by a people. This is the possibility of analyze the face is a first approximation because a person manifests his emotions also from his body, from the word used during a speech, and also from the voice. But first, usually, we look to the face, to the detail of the face. So, what are these emotions? And it is believed that, there are 7 basic universal expressions: fear, angry, disgust, happy, neutral, sad, and surprise. And here you can see some example of faces with the different emotions. The task in question is not new, and a lot of literature has been produced over the years. In particular, thanks to the recent advances in the field of machine learning and deep learning, many fear systems have been proposed and obtained, in some cases, high accuracy values, but still remain the following issues. First, it is observed that could be a significant overlap between basic emotion. And also, there is a difference in cultural manifestation of a given emotion. The biggest problem is that the public database used to train and test FAIR system are not large enough. This is the biggest problem. The available dataset differ in the quality of picture and how people express a given emotion. In some cases, people are posing with that particular emotion. A people is required to make an emotion, then the picture, I make a picture and label that images with that particular emotion. But in other cases, the pictures are in the wild. Namely, for example, the pictures are loaded from the web, and I annotate the picture with that emotion. And finally, the results depend on the databases used to train and test the models. In the intra-database protocol, the current method achieves accuracy around 95%. The intra-database protocol means that I have one database, and I split that database with train and test. In the cross-database protocol, the accuracy dropped down between 44 and 88%. This protocol means that I have 2 datasets, and I use one dataset for train and the other for test. And the things changes. Our attempt to solve the above issues and build a supervised classification method based on convolutional neural network is threefold. So we have these issues and we try to get around that issues with three steps. We enlarge the size of the training database, making use of data augmentation techniques, both geometric and guided augmentation type. We make use of transfer learning and fine-tuning techniques using pre-trained convolutional neural network models on the ImageNet dataset. And we apply extra database approach to measure the generalization ability of trained models, because we are interested in the generalization of our models. So, about the dataset. What about the dataset? We conduct our analysis making use of the following three databases. We use these three databases. The KDF with 980 pictures of posed subject. The CK Plus with 902 pictures of posed subject. And finally, the Jaffe with 213 pictures of Japanese female subjects. So, as I said at the beginning, to understand what kind of emotion a person is feeling, in a first approximation, we look to the facial details. So, all images are reduced to the square containing the face with a standard dimension of 224 to 243, where 3 are the RGB channels, and with the pixel intensity between 0 and 255. And to train a supervised classifier in the cross-database protocol, we take the KDF as dataset as a starting point in order to build augmentation, in order to make that data augmentation. And then we use the CK Plus and Jaffe as a test dataset. So, about data augmentation, we make two steps. The first step is use geometrical and color transformation, that are transformation that does not change the phase expression. So we build an operator making use of random rotation, zoom, horizontal flip, vertical shift, horizontal shift, and we applied this operator 5 times to each original images in order to get 4,900 synthetic images without with the same target emotion. So we do not change the target emotion applying this kind of operator. So we combine these images with the original one and obtain a new dataset that we called KDF-OL, where OL stands for offline, with a total images of, with a number of images of 5,880 images. In the second approach to make data augmentation is using GAN models. This approach has been already used in the literature. For example, by another Italian group of Porcu. This group used GAN framework implemented for the deepfake autoencoder architecture of the PhaseWhat project. What they did? They take the KDF images as starting point. They take 2 new images from the YouTube dataset, and they change. They make they swap the original phase with the YouTube phases, applying the phase of the YouTube dataset to the original one, but without change the expression. So they created 980 synthetic images that, once combined with the original one and the offline augmentation version, they created a new dataset called KDF-PFA with 6,860 images. We apply GAN models with in another way, building GAN models from scratch. So this is our pipeline. We group the pictures of the KDF dataset with the same expression. So we have 140 images with happy faces, 140 images with angry faces, and so on. To each group, we add 4 images of famous actors with the same expression taken from the web. For example, here we have the 4 pictures with happy faces that we add to the happy group, and so on. For each emotion, then, we have a set of 144 pictures that will be used to train a couple of DC GAN generator and discriminator networks to generate new synthetic images sharing the same facial expression. So, for each group, we train a couple of generator and discriminator networks. And I don't know, we believe that this procedure introduces a certain variability into the trained dataset. The train of the GAN networks. Thus, the produced synthetic faces will be slightly different from the parent faces in terms of pose, brightness, and background. Thus, for each emotion, we generate 150 synthetic images that we add to the original one and the offline augmented, and we get the KDF-Q dataset with 6,930 images. Here we have a recap of the training and test dataset. So these 4 datasets are the train dataset. The last 2 are the test dataset with the number of images contained inside. This dataset here, KDF-PFA-Q, is the union of KDF-Q and PFA. So with this dataset, we train our models. And about the models, we consider 4 deep learning architectures pre-trained in the ImageNet dataset. We choose VGG16, already used in the literature, the VGG19, Inception V3, and Inception ResNet V2 models. And here is a schematic picture of our models. We have the input images, the base model, so the pre-trained architecture, our task, namely the FAIR task, by using the knowledge acquired by the networks to solve a problem of image classification. Namely, the base model are trained on the ImageNet dataset in order to solve image classification. And the idea behind transfer learning consists in reusing the knowledge learned in solving a given problem and transferring it to solve a different but similar one. So we have a similar problem of image classification that is not equal to the original one, but we can reuse the value of the weights inside the network to solve our task. And we divided the training procedure into steps. In the first step, we freeze the value of the weights of all the n layers of the base model and train for 10 epochs the fully connected layer and the softmax function, so the top layer, with a learning rate of 10 to minus 3. So in the first step, all the base model is freezed. In the second step, we unlock the last k layers of the base model. So the base model has n layers globally, but we unlock only the last k. And we train these weights and also the output layers for 65 epochs with a learning rate of 10 to minus 4 in order to not move so far from the optimal position. We make this subdivision of the base model because usually lower layers identify lower order features, such as color and edges. And higher layers compose these features into higher order one, such as shape or object. Hence, to specialize the network to our task, we apply fine-tuning techniques, freezing the value of the weights of the first part and unfreezing, tuning the weights of the last layers. How we choose the number of the last layers? Because each model has a different number of layers. You can see here that, for example, the VGG16 has 19 layers. And we choose the value of k, making some train and validation tests, choosing the value of k, maximizing the validation accuracy. So for the VGG16, we tuned only the last 5 layers. And so on. To reduce and here we present the first result, where to reduce the influence of random weights initialization, each architecture was trained and tested 10 times. So, for example, we take the VGG16 architecture and train these models on the KDF-OL dataset. We train these models 10 times, so we get 10 models. And for each models, we calculate the accuracy and other metrics. So here we present the mean accuracy value and the standard deviation. We can see that the results on the CK Plus and Jaffe are completely different. The accuracy value in the CK Plus are quite high. In the Jaffe, no, they are bad, very bad. This fact shows the importance to test the models in at least 2 different databases, because we use this cross dataset protocol. And what is the problem here? The problem is that the CK Plus is a similar dataset, is a dataset similar to the trained dataset. It's different, but the picture inside is similar. Instead, the picture in the Jaffe are high biased because they are only Japanese female. They are high biased in terms of gender and ethnicity. So this shows the importance to use at least 2 test database. Anyhow, the generalization of our model is good because, for example, for the Inception ResNet V2 models trained on the KDF-Q dataset, we get a mean accuracy value of 86.15% with a close range of variation. Having a close range of variation means that the models are very stable. And we get a peak of 90.35%, the highest accuracy for the Inception ResNet V2 model. In this 2 table, I compare our result with other results in the literature. For example, here I compare the Inception ResNet V2 model. This is our result. This is a mean accuracy value. With other models tested on the CK Plus dataset. And I can say that our result is in the same wavelength of other results in the literature. We are in the second position. Although our peak is 90.35%. In this table, I resume for the best model Inception ResNet v2, trained on the KDFQ test in the CK+, that model that have a 19.35%, I show the precision and recall for each emotion category. And I can say that the model is good, although for angry and fear, we have a recall that is lower than 50%. That means that the model struggle to recognize angry and fear phase. Also, for the angry precision is quite high. So this means that when I say that, not me, the model, when the model say that the emotion is angry, that emotion is angry with a high probability. Moreover, we get for fear and sad a precision around 50%. That means that we have high false positive rate for fear and sad. So this means that angry, sad, and fear are probably the hardest emotion to distinguish, and in particular to disentangle between them. But however, this problem is a general problem for other models in the literature. The last experiment that we made is test the quality of the synthetic images that we generate with the GAN models. Namely, we checked if each group of images that we generate actually is classified as belonging to that class. In order to make this experiment, we choose the best classifier, Inception ResNet v2 and VGG19, trained on the KDF-OL, namely the dataset, this dataset 1, that does not contain the GAN-generated images, because we want to test that images. And for this trained dataset, we take the best classifier that are the VGG19 and the Inception ResNet v2. So, for each classes, we measure the accuracy value, and we have, for each classes, high accuracy, except for the sad phases for the Inception ResNet v2. But as I said before, the sad phases are difficult to disentangle. So, in general, thanks to the VGG19 models, we can say that our phases are good to use as train phases for other datasets. So this is my conclusion. We investigate various techniques to build an efficient supervised system able to recognize the human face expressions. The main obstacle to solve the task is the small size of a viable training dataset. And we get around this problem making use of data augmentation techniques and fine-tuning procedures. The experiment in the cross-database paradigm show that the Inception ResNet v2 model reaches a mean accuracy value of 86.15% with a peak of 90.35%, but suffer to recognize emotion like fear and sad. About the future, we would like to apply also transfer learning techniques to the data augmentation step in order to build high-quality images with GAN models. Recent works of NVIDIA, for example, shows that with pre-trained network, we can generate high-quality images. So we would like to use these pre-trained networks to generate faces with high quality to use then to train a classifier model. Moreover, in the work, we will also evaluate the influence of space and time context to estimate the emotion felt by a person in a certain instant. Because as I said at the beginning, we concentrate our attention to the face, but also the context where the people is embedded is important to estimate the emotion. But not only the context, but also the voice, the word. So these are all details that we can use to estimate the emotion. I finish and thank you.